Welcome back. Now it's time for us to proceed from cycles to processes. So let's make that transition and see what we discover. But before we do that, we have to discover, using the second law of thermodynamics, a very important property, the entropy. Let us proceed from where we left off with the Clausius inequality. The Clausius inequality told us that integral dq by t for any cycle is less than or equal to 0. But now let us look at the equality part of this, and let us separate that out. If we consider the equality part separately, we will be able to write that the cyclic integral of dq by t for a reversible cycle will be 0, and henceforth we will be using this subscript, either something like this or something like this, means this pertains to the reversible limit, either an R as a subscript or REV as a subscript. Now notice that this cyclic integral of this quantity dq by t is true for any reversible cycle, this equality for the Clausius inequality. Now since it is true for any reversible cycle, calculus tells us that this implies that dq by t for a reversible process element must be an exact differential. This is the second time in this course that we are encountering this discovery of an exact differential. Another way of reaching the same conclusion, which you will find in many textbooks, is as follows. Consider a cyclic process. You can select either P and V or x1 and x2 as the coordinates to depict it. Consider a reversible cycle. Since it is reversible, it is definitely quasi-static. And let 1 and 2 be two distinct states on this cycle. And let us say that 1A2B1 is one way of traversing the cycle. And this, the equality part of the Clausius inequality tells us that expanding this will be cyclic integral of dq by t reversible over the cycle 1A2B1. This is a reversible cycle. This will be 0. But now let us expand this as 1A2 one part of the cycle plus that over the second part of the cycle. Let me transpose a term, the second term, to the right hand side, and I will get. Now we notice, going back to the sketch, the process 2 to B to 1, 2B1 being part of a reversible cycle is a reversible process. So now if I execute it in reverse as 1B2, I am going to retrace the same path, but all my interactions are going to be reversed or going to be inverted. Whatever was dq will become minus dq and so on. So, the right hand side can now be written down as equal to integral of over 2b1 minus dq by t, which will be integral 1b2. Notice that the path has been reversed, it is being traversed in the other direction, and hence this minus dq will become dq by t. Now compare the leftmost expression and the rightmost expression. Of course, everything here is reversible, I should never forget that. When you compare these two, you will come to the conclusion that dq by t reversible, integral of this from 1 to 2 is independent of the path. And since now our cycle was any general cycle, and hence the process 1, 2 was any general process, reversible, 1, 2 were any two states. So, this implies that dq by t for a reversible process element must be an exact differential. Now, since dq by t is an exact differential, or integral 1 to 2 dq by t being independent of the path, both these things independently mean the same thing. There must be a property which is represented by integral dq by t, or whose differential is represented by dq by t, provided this dq by t is for a reversible process or reversible process element. That means this should represent the differential of some property, or this would represent the change in some property from state 1 to state 2. This property, or this property, which is the same property, we define this property as the entropy of the system and give it a symbol S. Thank you.